Hello, everyone. I wanted to just give you this breakdown as to how to draw Lewis dot structures for molecules and polyatomic ions. Fortunately, you've got a chemistry teacher with you right now that can help you with this, but I really wanted to start the lesson myself, okay, and just give you the breakdown as to how I like to approach these things. And then you'll be given a worksheet, and the teacher that's in the room will be able to help you if you have any questions, okay? And by the way, if you have any questions while I'm doing this video, the teacher can stop the video and that teacher can answer your questions in real time. So anyway, let's get started. I want to show you a systematic way of approaching drawing Lewis dot structures, and I really think that the best way to do this is to just go into some examples and to tell you what I'm doing every step of the way. So let's start this process. We're going to do this in steps, and I'm going to ask you to follow these steps whenever you're confronted with a chemical formula that you need to develop a structure for, okay? So you're always going to be given a chemical formula. It's going to be your job to decide what that molecule is going to look like, okay? The first step that we're always going to follow is we're going to count the number of valence electrons in the molecule. Okay, so I just did this for, this is hydrogen fluoride, by the way. I did this for hydrogen fluoride, and hydrogen has 1 valence electron. Fluorine has 7 valence electrons. Okay, when we add those electrons up, we get a total of 8 in the total molecule of hydrogen fluoride. The next step is to draw a possible skeleton structure using covalent bonds. I'll show you what I mean by a skeleton structure. Okay, so this is a skeleton structure. This is just about the only thing that you could do, really, is draw a chemical bond, which is this line. This is the covalent bond between the hydrogen atom and the fluorine atom. And it's what you need to do now is remember how many electrons make up a covalent bond. That's 2 electrons, right? It's a shared pair of electrons. So out of the total number of valence electrons that we've got in this molecule, we're going to use 2 of those electrons to make this bond. And then we're going to see how many electrons are left over. Okay, so out of my bank of 8 total electrons, I used 2 electrons in the covalent bond. That left me with 6 leftover valence electrons. We're going to take these leftover valence electrons and distribute them around the fluorine. Now remember how important an octet is to stability, right? So what we're trying for here are octets all the way around the molecule. We're trying to have stable atoms within that molecule. Now, if I draw a circle, an imaginary circle around this hydrogen atom, that hydrogen atom has 2 electrons. It's got the electron configuration now of helium, which is stable. Remember, helium is a noble gas. All right, what about the fluorine? Okay, now watch how I'm drawing this imaginary circle around all of the valence electrons around fluorine. That's a total of 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. That's 8 valence electrons. This is an octet of electrons around fluorine. What we have now is a stable molecule. We have octets all the way around, so we know that we've got the right answer. I should have included another step there. I just talked through the step and I didn't say, hey, step 3 is check for octets around the atoms. And that's what we did just previously. Okay, if we have octets all the way around, we've got the answer. All right, So let's try some other examples, and then I want to get you started on your worksheet. Okay, let's try water. Okay, good old water. Now, we've got 3 atoms here in this molecule. We've got to decide which atom is going to be in the center of the molecule. Hydrogen, by the way, is always going to be one of those atoms that surrounds a molecule. Hydrogen could never be a central atom. And, as we do some examples here, you'll see why. You'll see it right here in water. So, like I said before, we're going to start with counting the number of valence electrons in this molecule. If we count the valence electrons, that's 1 valence electron for hydrogen, another valence electron for hydrogen, and 6 valence electrons for oxygen, giving us a total of 8 valence electrons. If we draw a skeleton structure now, all right, oxygen is going to be in the middle, and we're going to put hydrogen around the outside. You could try this yourself, but hydrogen can only form a single bond ever. So hydrogen is always going to be a surrounding atom, but you could try it yourself and see if you don't break any rules trying it. This is going to be our skeleton structure for water, H2O. Now you can see that I've used up 4 electrons making these covalent bonds. That's 4 electrons that we've used. All right, we're going to subtract that from our bank of 8 electrons. 4 electrons were used for covalent bonds, leaving us with 4 leftover electrons that we need to distribute around this molecule in order to make an octet. All right, so watch what I'm going to do here. I'm going to put a pair of electrons there and a pair of electrons there. And now what we have, if you'll follow my laser pointer, we have a total of 2 electrons around this hydrogen. That's an electron configuration of helium. That's 2 electrons around this hydrogen. That's the electron configuration of helium. And we've got 8 electrons around the oxygen. That's the electron configuration of neon. Okay? We've got stable, stable, stable. We've got octet, octet, octets all the way around this molecule. We've got the right answer. And this is our Lewis dot structure for water. This is the answer. Okay, let's try another one. Let's try ammonia, NH3. Okay? Let's start with counting the valence electrons. All right, so nitrogen has 5 valence electrons. Hydrogen each has 3. So the hydrogen altogether, that's 3 valence electrons. That's a total of 8 valence electrons in the ammonia molecule. All right, next step. We're going to draw a skeleton structure. All right, I'm going to put nitrogen in the middle. I'm going to put the hydrogens around the outside. There's our skeleton structure. There's really no other way to make that happen. And what we used in that skeleton structure is 2, 4, 6 electrons. So we're going to subtract those 6 electrons from our bank of 8, and it's going to leave us with 2 leftover electrons that need to be distributed around this molecule. I'm going to put those 2 electrons around the nitrogen. And what we've got here now is called a lone pair of electrons. This is the first time you're seeing that, so I am going to really label that. This is a lone pair of electrons. Okay, that says lone, L-O-N-E, if you can't read that. All right, this is going to be very, very important when we're looking at shapes, which we're not going to do today, but that is going to be an important aspect that's going to come up over and over again. So that's why I'm labeling it right now. You should really pay attention to that. Now, let's take a look at, did we create octets all the way around? All right, 2 around hydrogen, yes. 2 around hydrogen, yes. 2 around hydrogen, yes. What about this 1, 2, 3, 4, 5, 6, 7, 8 around nitrogen? That is an octet around nitrogen. That is the noble gas configuration of neon. Okay, right there. Okay, so we've got the answer. That is the Lewis dot structure for ammonia. Let's try one more. Okay, let's try methane. Whoop, that's not what I wanted. Let's try methane, CH4. Okay. All right, counting valence electrons. So valence electrons for carbon is 4, and each hydrogen has 1. So the hydrogens are contributing 4 valence electrons to this molecule. That's a total of 8 valence electrons total, right? What about our skeleton structure? All right, there's carbon 1, 2, 3, 4 bonds. I need 4 bonds because I've got 4 hydrogens. Guys, by the way, before I go on, let's make sure that you understand that putting a double bond on a hydrogen, wow, that's really totally illegal, right? I mean, take a look. How many electrons, if this was something that you were proposing, look at how many valence electrons are around hydrogen right there. There is no possible way that that hydrogen can hold 1, 2, 3, 4 electrons. Not possible. Impossible. Let's forget all about that. All right? Please don't ever show me a double bonded hydrogen. Okay? All right, let's move on. So what have we done here? Oh, by the way, I'm going to get rid of this. Okay, so let's finish this up. So we're using a total of 8 electrons for these covalent bonds. Okay, that's 2, 4, 6, 8. So that means we used up all the electrons in our bank. We're not left with any leftover electrons. Therefore, that is our Lewis dot structure for methane. So these examples are pretty simple molecules. You're going to get better at doing this with practice. I want to show you some other, maybe a little bit more complicated examples now, okay? Just briefly, but I want you to remember there is such a thing as double covalent bonds and triple covalent bonds. I want to give you an example of doing a Lewis dot structure with a double bond. Okay, let's try this compound out. And while we're doing this, I'm going to write some general rules for you. Okay, one rule is this. When it comes to carbon usually always has 4 bonds. You really should write this down. Oxygen tends to have 2 bonds. Nitrogen tends to have 3 bonds. Okay, hydrogen can only have 1 bond, of course. We already mentioned that. Okay, so these are some general rules that you might want to keep in mind. Here's another rule that I think is going to come in handy. Carbon, and I'm just going to write a note here with carbon, it's usually the center atom. So let's try this compound. Let's see if we can come up with a structure for this. Let's use the procedure that we had before and then see if these simple rules apply to what we just did, to what we're doing, okay? All right, so we're going to count up the valence electrons. All right, we've got 12 valence electrons total. We've got 1 from each hydrogen, 4 valence electrons from the carbon, and 6 valence electrons from the oxygen. Altogether, we've got 12. Let's put together a skeleton structure now. And I've got a carbon. I'm going to put it in the middle. I've got carbon connected to oxygen. I've got hydrogen connected to carbon, hydrogen connected to carbon. Okay, but looking at this, this can't be the final answer. All right, we can't have just 6 valence electrons around carbon. That's impossible. So let's take a look at what we could do here, right? One of our rules up there, the simple rule that I gave you, is that carbon usually likes 4 bonds. It's only got 3 that we've got in our skeleton structure here. Oxygen tends to like 2 bonds, and we've only got 1 bond for this oxygen. So wouldn't it make sense to try a double bond here? Okay. And let's give this a try and see if this works out for our valence electrons. All right. I used two electrons in this bond. That's 2 plus 2 is 4 plus 2 is 6 plus 2 is 8. We used up 8 electrons. And we've got 4 valence electrons left over. And what we're going to do now is distribute those valence electrons so that we have octets all the way around. I'm going to take those 4 leftover electrons, and I'm putting them around the oxygen. Why am I doing that? Because if I do that, now I've used up all the electrons in the valence electron bank, and I've got an octet around the oxygen. I've got an octet around the carbon, and I've got 2 around the hydrogen, which is an octet for the hydrogen, and another 2 electrons around that hydrogen. So we've got our answer there. Okay, guys, so one last one. All right, I want to show you a polyatomic ion. And one way to think about polyatomic ions is to think of them as molecules with a charge. Okay, here's an example. Let's go with the sulfate ion. Okay, and let's just see how this is just a little bit different than what we did with those neutral molecules previously. Okay, what this means is we've got 1 sulfur, 4 oxygen, and 2 extra electrons being added to our valence electron bank. Okay, so what we've done here is we've tallied up our valence electrons. I have 6 for the sulfur. I have 4 oxygens, and each oxygen has 6 valence electrons, so that's 24 altogether. And I'm adding 2 extra here. Okay, so this is going to give me a total number of valence electrons of 32. Okay, that's 32 electrons in our bank. And now we're going to spend some electrons putting these bonds together. Let's see how we can do that. I'm going to start with a skeleton structure, which brings up another point. Now, you notice that I put the sulfur in the middle. This is hard to put into words, but at least for me anyway. So when you're looking at a situation, let's say, for instance, where we've got 1 sulfur and 4 oxygen, we're going to put the atom that represents the least number of atoms in the molecule or polyatomic ion. We're going to put that least number in the middle. Okay, in other words, I'm not going to put oxygen in the middle and then have sulfur, one of the surrounding atoms. Okay, so I'm going to choose the atom that represents the least number of a certain element and put that in the center. It's harder to put into words than it is to just show you. So here we are. I have sulfur in the middle, oxygen surrounding. I hope you really understood what I tried to say there. Anyway, what did I spend here as far as valence electrons? I used 2, 4, 6, 8 valence electrons. So I take 8 electrons away from my bank of 32, leaving me 24 electrons now to distribute around this polyatomic ion. So I'm going to just do that now. Okay, so there I did it. I took those 24 electrons and I distributed them around this molecule in order to get octets. Notice how I've got an octet around each oxygen now, and I have an octet around that central sulfur. Okay, now we're not finished because this is an ion, and you cannot forget that this is an ion that has a 2- charge. All right, so what I've drawn here are brackets around this this polyatomic ion. The brackets, guys, are important. It's not just some extra fancy thing that I'm adding to this. You have to show that this is an ion, all right? I told you before that molecules and ions are very different things, and atoms and ions are very different things, right? There's a profound difference between a molecule that is neutral and a polyatomic ion that has a charge. There are huge differences there, and you can't forget about them. Okay, so this is the final answer. This is our Lewis dot structure for the sulfate ion. Okay, that is enough. I'd like you to get started on the worksheets that we have for you. And your teacher that's there can help you. Thank you, guys. Bye.